So good evening, everyone. I'm Andrea Urgolo, and I'm going to present you Learning to Monitor, a novel framework for online system verification. This is a work jointly made with Dr. Andrea Brunello, Dr. Dario, and Professor Angelo Montanari. In many domains, during its execution, a system generates several continuous streams of data, which may contain helpful telemetry information that can be used for tasks like predicting maintenance and preempting failure detection. However, system behaviors can be convoluted due to interaction among several components and the surrounding environment. Given this complexity, in the last year, deep learning approaches like artificial neural network have been used. However, this model has some drawbacks. They are hardly interpretable and they cannot easily provide guarantees on the obtained results. So in critical context, formal methods are used to provide guaranteed on the correct behavior of a system. However, in a real-world scenario, a complete domain specification of all properties that have to be guaranteed during the execution of the system is often out of reach. And also it is difficult to derive a complete model against which we can check the properties of interest. To overcome this limitation, we design a framework which pairs machine learning and monitoring and is able to learn interpretable formal properties and to deal with complex system behaviors. Okay, this framework operates in 5 main phases. Firstly, we specificate an initial set of properties. Here, domain experts are asked to specify some properties that characterize the desirable behavior of a system or undesirable behavior. And then we can start the monitoring of the system. In the next 4 phases are the main phases that are executed during the monitoring, during the execution of our framework. And so we start the monitoring on the execution traces of the system. Then we detect an eventual failure. When we detect a failure, we try to mine relevant behaviors pattern related to that failure. And with the pattern obtained, we extend our pool of properties that we can use to characterize failures of the system. Okay. The framework works in an iterative way, and for each iteration, we consider a different execution trace of the system. There are 2 main modes of execution. In the warm-up mode, we analyze data from past system failures. And in the online mode, we monitor the current behavior of the system. So in our implementation, we use linear temporal logic to encode the temporal properties. And the execution traces of the system is made up of time series. And we have one time series for each sensor of the systems. For example, a time series could be seen as an output of a sensor or as a data taken from the system log. And we convert this time series using the SAX library because we are working on prepositional variable, and to be able to use linear temporal logic, we need to discretize our time series. Okay. So let's see in more detail how this monitor works. At the beginning, we have an empty monitor pool. We add just a single trivial system is in operation property. And then we start the system feeding the framework with the incoming data, one point at a time. So we consider the last a time window with the last values of each timeline. And against this time window, we match all the properties that are present in the monitoring pool. When a property matches these time windows, we have a failure detection. And so when we detect a failure, we derive two different subtraces from the current execution traces. The failure window, which is the portion of the time series that immediately precedes the failure event, and the normal execution trace, which goes from the beginning of the timeline from the last until the failure windows. Starting from these two sets of traces, we exploit a probabilistic Bayesian generative model, which is called Bayesian LTL, to extract LTL properties that are able to distinguish between failure window and normal execution traces. This tool is based on some LTL formula template, which are instantiated with all the possible values, or a subset of the possible values of the propositional variables. After this step, we obtain a set of LTL formulas, and these formulas are combined by means of a decision tree model, which is trained to distinguish between these two kinds of traces, failure traces and normal execution traces. The basic idea here is that if we use a 100% accurate approach to extract LTL formula, the complexity of the algorithm is too high. So we use a suboptimal algorithm that give us some LTL formula that are not 100% accurate in distinguish between failure and normal execution traces. But we combine this obtained formula with the decision tree to obtain 100% accuracy. And so we can keep the complexity linear with reference to the number of traces and the length of the traces. So once fitted, we put the decision tree in the monitoring pool, and we restart all the monitoring processes with new system execution traces. We evaluated our framework on the CMAPS dataset, which is a CMAP that contains rounds to failure execution traces related to turbofan jet engines. And as we can see on the graph here, going on with the iteration, the framework can issue early failure warning in a more preemptive way. So here the blue line is the remaining useful life of the failure warnings, of the failure prediction. And we can see that it increases its values when we go on with the execution of the framework. And these are the most important issues that we encounter: remaining useful life estimation, stopping criteria, and false positive. Actually, we predict remaining useful life relying on statistics. We have statistics for each properties that we put in the monitoring pool. We keep track on the failure point that triggers that property. And but in the future we plan to develop a metric for remaining useful life estimation. And as stopping criteria, we use two thresholds. One is based on the maximum decision tree height, and the other is based on the minimum extracted properties accuracy. And last but not least, this is one of the main problems, false positive. And we try to evaluate our framework also with other data set that has some good execution traces. For example, the smart telemetry dataset from hard disk has some good execution traces from good hard disk, and we can use that kind of dataset to evaluate our framework with reference to false positive rates. And we have tried some strategies to reduce false positive. One is data augmentation. So we take the original execution traces and we generate a new execution traces, applying some transformation to these original execution traces. And we think that this could help to extract properties that are more related to the failure. And another strategy that we are investigating is feature selection. So we try to remove time series that are not so related with system failures, and that exhibit patterns that are repeated over the time, so they are completely useless for our objective. Okay, and with this I conclude the presentation. In the future, we are planning to improve and extend our framework. We must evaluate different properties extraction approaches, try different logics like signal temporal logic, Alper-Schoen model logic, and so on. We have to evaluate our framework on different data sets and to compare the results with other state-of-the-art predictive maintenance approaches.